So our next speaker is Balazs Gerofi. There are a lot of Hungarians this morning. So my parents were Hungarian. Used to be a guy who say, my brain is open, Erdős. There is a fascinating book about his life. If you think that you're a nerd, read about Erdős. That's beyond. So Balazs, he started. Balazs is another recommendation from Bob Wisniewski. So, and came to Multicore World probably 10 years ago, or more or less.
It wasn't 10 years ago, I think.
Yeah, probably.
18 or 17.
No, it was 16, 17. You came a couple of times. And I teased you yesterday that now you stay in good hotels, and then you were a student. Anyway.
Okay.
So he's from Intel now. Used to be at Riken.
Okay, so thank you, Nicholas, for the invitation, and thank you all for sticking around on Thursday. And so I'm going to talk about something that is not going to be very mathy. It's more on the computer science, but I would even say that it might be even just engineering. So it's please bear with me. The topic is failure management in large-scale systems, and so this is a somewhat sensitive topic from a vendor, and that means I'm not going to be able to show all that much data, and I will also have to anonymize certain things, but I hope that it's still going to be something that you will enjoy. So I just need to put this up here. And so what I would like to do is to first motivate this work and then give you some background on failures and also on the system that on which we did this study. It's of course Aurora. And then I will talk about the architecture of this automation framework that we built and how it's working and what it is doing, and then show you some results. And so let's start with motivation. So I think people in HPC are not unfamiliar with these things, but as systems grow larger, of course, we start seeing failures in higher frequency. And this is something that has been predicted more than 10 years ago in the HPC community. And just as a shameless plug for Multicore World, I think several of the people on that paper actually have talked on this conference. And so this is something that I think is today, it's fair to say that it's really happening. And interestingly, similar to the story how system noise went with HPC to the cloud, failures in large-scale systems are now also discovered by the AI community. And they have been making some noise about how they cannot do their training, and which is basically an HPC problem. And and they have made actually very interesting predictions how, as they continue scaling, building these larger systems, what kind of problems they might run into. And so, of course, this is an issue that is particularly problematic with these large coupled parallel workloads, because they use the entire machine, and once a single component goes down, then the whole run goes down. And this is not so much of a problem in a classical cloud setup where you have like redundant microservices where some parts of the application can just automatically take over pieces of the execution. And so, for instance, the meta paper where they talk about this problem calls these nodes the lemon nodes that eventually ruin the whole run. And so I'm going to talk about an automation framework that I think might be increasingly necessary in this kind of systems. And just to be fair, this is not about how you avoid failures, it's more about how you deal with them. And so there are different dimensions to this topic. Okay, so I just wanted to show you how Aurora looks like. I think many of you are familiar with this. The heart of it is are the two main execution units. One is the CPU, which is a Sapphire Rapids with HBM, and then the Ponte Vecchio GPUs. And so you build compute blades out of these, where you have 2 CPUs on a node with 6 GPUs and 8 network interfaces. So you take a number of blades with some switch blades, and then you build these racks out of it. And in Aurora, you have 64 compute blades in one rack, or they call it cabinet. And of course, you have all the other infrastructure around it, like the power delivery and the cooling and so on. And then 3 racks form a logical unit from the perspective of cooling. And eventually, you build the whole system out of this. And so in Aurora, there are 166 of these cabinets, which equals to 10,000 or 10,600 compute nodes. And so if you just list up all these different components in the entire system, you see that these numbers are large. So you have over 10,000 compute nodes, you have over 60,000 GPUs, 20,000 CPUs, 80,000 NICs. And then there are all these other components in it, in the node, like the DDR, DIMMs, and so on, which the point is, in particular for this talk, is that, so at the end, you end up with over 345,000 parts in the system that are replaceable and to some extent repairable. And so these are, so there are many implications of this. I think one is that this is a large enough number that you want to be extremely precise how you track things on it, so that you are very aware of under what conditions, what happened on the system, and you can make decisions based on that. And then also there is this thing related to the repairability, is that many of these parts have diagnostic tools to them that you can apply in the field without removing them from the system, and potentially repair some issues. And so that's very important that is efficiently utilized. And I will talk a little bit about that. So I wanted to give you a little bit of an overview of how we see different type of failures in terms of how you could classify them. And so I must say, first of all, that if we want to be extremely precise, then I would need to talk about faults, errors, and failures. But for the sake of simplicity, I'm going to consider everything just as a failure and then categorize based on that. And I must also say that this is somewhat outside of my expertise, so I appreciate the people in Intel who helped with this. And I just want to show you some example of some illustration of how one way of thinking about it. And so what you see here is you have time on the x-axis, and then the blades, the compute blades in the system on the y-axis. And so one of the failures you could classify that are mainly due to design bugs. So these are the one particular characteristics of these kind of failures is that if you hit the right condition, then typically they would fail on every part, every instance of that part in the system. And so with HPC, very often what you see that this happens is that you run some kind of exotic workload that you have never really tested before, and then some parts fail almost at the same time in the system. And so this is the one good aspect of this, if you can call it good, is that usually if you go after this condition and you figure out what was the right, like workload that was executing, then you can actually create a reproducer. And usually you can create a reproducer that even causes this issue on a single part. And this is good because that means then you can take it and you can examine it and eventually work around it. Like you can do a firmware workaround or some software workaround and eventually solve this problem. So okay, so there is this, and then on the totally opposite end of the spectrum there is something that people call transient errors. transient failures. These are often considered to be coming from outside impacts, like, for instance, various radiations or cosmic rays. I think people hear about this often in the context of memory, like DRAMs producing silent data corruption type of issues. And so this is something that usually just happens in some somewhat uniform distribution across the entire system. And one thing that you know about it is that based on the parts, you have some sort of expectation of what distribution you can expect. And so the only issue with this is that when you see higher frequency than what you expect, because then the question is that, well, why is that happening? And so this is one. And then there is one between these two, which is the most problematic one, which is called intermittent failures. And so this can be due to various different things. Like, for instance, it can be due to degraded or aged components, but it can be due to more systematic issues, like marginalities that are related to frequency or voltage. And also it can come from manufacturing defects. But the real problematic issue with this is that usually you cannot reproduce them. So they appear sometimes, but even if you take the same part and you do the almost, you try to do the same condition in terms of what you execute on it, it usually doesn't reproduce, or it takes a very long time before it reproduces again. But so one thing with it is that, and I just want to go this far, is that if it does reproduce even across longer time periods, then that's a strong indication that there might be something wrong with the part. And so that's one way of sort of trying to distinguish it from transient errors, but of course that's also not something that you can say with 100% certainty. And then there is this other, this fourth category, which I just put up here because we have seen these kind of things, is that when you see failures, like correlated failures that appear to be a hardware issue, but when you look into it more in detail, then it turns out that it's actually caused by some software or something related to networking or some other external effect that you can eventually find out what's the reason, and you can make the conclusions that that's not related to the hardware itself. Okay, so you see that there are all these different type of failures, and so you want to be very careful to understand what's going on in a large scale system like Aurora, and how you deal with this. And so here are some observations on this. So first of all, you may ask the question, how do you distinguish between intermittent and transient failures? So unfortunately, the answer is that there isn't really any reliable way of doing it, especially when you see it happen first time on a part. And then, so how do you handle all these first strikes? And I'm calling strikes on the previous slide where when the failure happens on a particular part. So how do you deal with them? Replacing every single component on which you see a strike is impractical, and it will cost a lot for anyone operating such machine. So you need to do a somewhat more sophisticated approach to this. And so as I mentioned, the probability of an intermittent failure to happen on the same part again is extremely small. So if you see such things, then that's a good indication of there might be something wrong with the part. So that's something that you want to keep in mind. And so in order to deal with these in a somewhat more statistical way, we need to understand the reoccurrence rate of the different type of issues, and also how much time you spend between they come back. And so these are very specific to different failure modes, and I will talk about that later on how we deal with that. So the point is that you need to capture the history of all this information in context, so that you can make these decisions how you deal with the different type of failures in real time. And obviously you want to automate this, and then the question is that how far can you go with automating the overall process? And okay, so let me move to the. So I'm going to talk about this software infrastructure that we built to deal with these issues. And it's a somewhat unfortunate name, but we called it a stability database. And so it has many components to it. You can see it starts on the left with okay, this is not visible there. But you start on the left with the system, and the infrastructure collects various metadata that I will talk about more detail in a second on the different parts in the overall system, and it also captures failures automatically. So it listens to various different data sources and identifies when a failure occurs. And what we do is that we then collect various information that might help to describe what happened. And this is something that I think may be somewhat related to the PVC architecture, but there are certain failure informations that get logged into these circular buffers that you need to capture at the time when the failure happens, because otherwise later on you might lose it. So the point is that at the time when you see some issue, you need to go and collect various different information on it, and then we put them all this together into bundles, and on that you can then do these automated triage. And so what we do is that this runs contiguously and monitors the system and saves all this information, of course, into a database. And then once you have that, then you can do all sorts of things with it. And so like you can do, you can look at different failure rates and visualize different type of issues and just look at like the history of a part, for instance. And so in essence, this database is like a metadatabase of the various events that happen on the system, and it captures currently failures. It also tracks all the inventory and various different components in the system, which I'm aware of that there are other tools that do this. But you want to put all these things together. The point is that you want to have them in an integrated way so that you can look at the entire history so that you can make real-time decisions. And so it does, it tracks also other things like versioning on firmware and various software pieces, and also tracks workloads to at least to the extent we can get visibility into that. And it also tracks information related to the resource manager. And this is something that, of course, can depend on what sort of resource manager you use. But in case of Argonne, this is a PBS scheduler. And with this one, you can then easily do, real-time analysis, and you have all this data in a context. Okay, so if we look at how this actually, and this is a bit of more on the implementation side, how it plugs into the various different pieces on the Aurora system. So it's not intended to replace any of these existing logging infrastructure that is already operating on the machine. It is supposed to be just collecting a higher level summary type of information of all this data and picking up the right pieces. And so it plugs into various pieces there. I'm not going to go on all the details, but again, the point is that it does not intend to replace any of this. And so I have another slide on some of its functional breakdown of what it's doing. And one thing I want to just emphasize here is that, so we did, other than all this tracking, we did some other functionality that, for instance, it can automatically detect if some jobs are hanging, and then it would go and collect various information like stack traces of the application and so on. And it was somewhat interesting to see that at the time when the meta paper came out, they actually talked about exactly the same issues, that they had to build, they had to do extensions to various runtime pieces to be able to do this. So it seems that these issues are increasingly popping up on these large-scale systems, but there isn't really like a standard solution to it. And okay, So I'm going to talk about something here that we call a multi-strike policy. And that's really at the heart of what the automation does when it sees certain failures happening. And for that, I show you this. This is a data that has been collected over 6 months. And so on the x-axis, you have different type of failure signatures, and these are all anonymized. So it's not, we have more precise names on what the certain things represent. And then on the y-axis, you see the time you spend between the first and the second strike on the same part. And plus, so that's on the left y-axis. And on the right y-axis, you can see the reoccurrence rate. That means that like how many percentage or how much percentage of the parts that have seen an issue like this eventually see a second one. And so you can use this kind of data to drive the way how the system deals with these various issues. And obviously what you want is that you want very low reoccurrence rate. If your reoccurrence rate is very low, then you say, then it makes no sense to replace that part when you see it a first time, because it may be fall into this regime of the transient error, right? And on the other hand, if you have a relatively higher reoccurrence rate, then you could make an argument that, well, you may want to use the part if you have a long time before a second problem would pop up, because then you can still productively use that part. And you can go, you can be whatever fine-grained you want and decide the policy, what you want to do based on even the particular signature. And actually, that's mostly what we are doing. That for every signature, there is on the hardware side, there is someone who is responsible, saying that, okay, does it make sense to keep a part like that in the system or not? And so I just want to highlight one of these here. So this is, for instance, related to the GPU HBM. And you can see that it has a very low reoccurrence rate. And in the median, it would last more than close to a week before you would see a same problem. But sometimes it takes months. So it's really, it's really it's not economical to remove immediately when you see a problem like this. And the other thing is that I mentioned this. Mentioned the fact that there are these in-field repair diagnostic tools. So many of these parts have their own in-field repair diagnostic tool. And that means that when you see, for instance, an issue for the first time, you can go and potentially repair that part in a way that then it will turn into something as if it was a new part. Like there are spare processing elements, for instance, on the GPU, and you can rewire the firmware that it will use parts that it will hide the part on which you saw an issue previously. Okay, so for instance, just to demonstrate this overall multi-strike policy, I show you a table here where I only show the one that I highlighted on the previous slide. And you see that so for this GPU HBM issue, for example, for this particular problem, what we would do is to run an in-field repair tool on it. And if that can fix something on the HBM part, then of course it can go back. If not, then we will see, based on the statistics, we will still give it another chance and see how far it can stay healthy in the system. And so these are, again, based on, for every single failure signature, you can build a different type of, this is like a plan of what you will do when you see such issues occurring. And the point is that you want to make these decisions based on the statistical information that you collect over the lifetime of the system. And of course, this can change over time. I'll show you later that some of these actually have started dropping significantly. Okay, so using this, then what we built is a full automated system that will actually go and interpret these policies and do certain actions on the blades. And so again, you have your system, you have all this tracking infrastructure, and you have the implementation of this strike policy. which looks at the history of the entire system, in particular for those blades, or it even can look at like correlated issues that you need to handle separately, and then it can execute these actions that are specified in the policy automatically, and it does all sorts of in-field repair tools, but it can also do when it realizes that okay, there is nothing else and you can do then it can ask like that someone from a human maintainer need to look at it and make a decision, or it can automatically submit tickets to the operation team at Argonne that they need to, let's say, swap two teams or things like that. And so this is so you see this is more on the side of bringing up a large system and then eventually to efficiently operating it, rather than the, you know, it's not a, as I said in the beginning, it's not so much a scientific contribution here. So okay, so I would like to show some numbers that what we could see with the help of this system. So on the left side, you have the distribution of time that is spent on blades that are handled manually versus that are handled by the automation system. And so you see that in average, or not average, but the median time that manual disposition took. This was, by the way, at the time when the Aurora acceptance test was running, which was about a 3 to 4 weeks period. And so you see that from let's say roughly around 60 hours, the time that it takes to deal with blades went down to 0.7 hours. So this is a huge win for the operation team and also from an availability point of view, because then these blades can come back to the system a lot faster. And so on the right side, you can see that that as we build more and more, as we implemented more and more actions and enabled these actions, how the different failures are handled, eventually the automation could handle a very large part of the different issues that we saw. That's on a per day basis. And you see the relative, basically the ratio of in percentages of how many issues were handled by automation. And so going back a little bit to the left side, you may ask, well, why is it taking 60 hours? I mean, I agree, that's a horrendous number and it should be a lot more efficient. But in reality, there are so many components to this that people need to go and figure out what happened, and they need to go through various bureaucratic procedures like putting in a ticket or whatever to another person that will deal with certain steps, and eventually that adds up. But if of course you do this all from software, then this can happen a lot faster. And okay, so another thing I wanted to show you is this is the availability and utilization plot during the acceptance test. And so Argonne's requirement was to stay above 95% of the availability, and we could stay above 98.4%, so we could easily meet the requirement. And of course, this was by large contributed by this automated system. And I should also say that the system wasn't entirely full, and we didn't have the luxury to have hundreds of spare parts hanging around that we could just swap in. So this was important that every single issue was dealt with as quickly as possible. And so here's another plot that shows some of the evolution of these issues over time. So on the x-axis down there, you have months, and then you have the counts for second and first strikes on these different issues. And you can see that many of them are trending down. So we are very happy about that, obviously, because that means that the overall stability is increasing. But on the other hand, there are some which stay pretty much constant. And for instance, you can see some of the HBM issues. Those are the ones that we keep seeing, and And I've heard this from other people who run other systems that they have similar issues, but so that's unfortunately something that we cannot do too much about. And so here's another thing I wanted to show, and I'm actually getting to be close to be done. So this is a breakdown of the various different problems that we saw during the acceptance period. On the left side, that's the Aurora story, and you see that, well, so you can basically disregard the performance only issues because those are not like hard failures. But for the rest, you see that we have a lot of problems, of course, with GPUs, and then we have hangs and stalls. We had issues related to the fabric, and then you go on, you can see all the breakdown. And so what is really interesting is that, again, this was around the same time when Meta published this paper, and they provided a breakdown on their cluster, and actually they are seeing almost exactly the same problems. And even the breakdown is very similar. And so this was somewhat reassuring for us that, okay, well, this is maybe not only our problem, but this is something that people see more generally in the field. And the other thing, without saying anything about Aurora MTBI, I was very explicitly asked not to do that. I just want to say that the Meta paper actually does projections, and they even project out to the scale where we are on Aurora today. And they say that they wouldn't be able to run more than an hour on that system if they build such a large scale system out of those parts. So clearly there is something that we need to do about this, and I think this. So what I'm talking about is could be one step at least towards helping to automate pieces of it. And so I wanted to put this up here just as an outlook type of thing, that there is a lot of interest recently. Of course, we heard several talks about digital twins in this meeting as well. But there is, of course, a lot of interest in building digital twins for supercomputers and data centers. And so I feel like the automation or the overall system that I talked about here is something that could very well be part of this, because they even explicitly state that some of their goals is to efficiently maintain and repair the system. And and this is, again, and the other thing that I found interesting is that they really stress on the fact that you need to put all this data into a single place where you can have everything in context, and you can easily relate to each other with respect to what is happening on the system. So I think they are mostly, as far as I've seen, they have mostly been focusing on thermal and power effects, but you could easily imagine plugging this aspect into the overall digital twin story. Okay, so I'm going to just real quick summarize what I talked about and maybe mention a few points what could be done in the future. So, of course, as large-scale systems grow in size, we see more and more of these intermittent failures that are really problematic to deal with. And in order to minimize downtime and to maximize usability of the system, you want to, of course, automate as much as possible. And for that, you need decisions that are driven by data and not by just some feeling of whatever, I don't know, designer people of what could be done for certain parts. And for that, the key is that you need all this data in context and collected over time and very precisely queryable in a way that it can be real-time, you can do real-time decision making. And so I didn't talk about we have started looking at how we could actually use all this information to do predictive avoidance of failures, because of course that would be the ultimate plus, where you can just say that, well, don't use that because you will most likely hit a problem. And there are also other orthogonal aspects that people consider, like you can do continuous screening of all these different parts so that you make sure that you maybe catch something earlier than an application hitting the problem. And just thinking a little bit further out, I think one of the issues that we see here is that there are all these different parts in these large systems. It's a really complicated system and come from various different vendors. And the way how the error or failure reporting is done is not standardized. So you cannot easily build a system that then if someone brings a new part, you can just plug it in. So it would be really nice if there was some steps even in the direction where there is a standardized interface that you can plug in and then drive such an automated system. And so there were many people involved here. I just wanted to put the name of the list of the names here, even some of the Argonne people. And with that, I thank you very much for your attention. Thank you very much.